Hey guys, welcome to another lesson, and we're going to start off with our doing a question. So if you want to pause it here and have an attempt, that would be amazing, and I'll go through the answers. I'll read the questions out to you now. In the last lesson, which hasn't happened yet, I haven't actually done the experiment. I'm setting up my state-of-the-art laboratory in my garage, so that hasn't happened yet. So you're getting a sneak behind the curtain here that I haven't done the experiment as I record this video. But by the time you watch it, you'll have seen me do the experiment. That's the beauty of doing videos online. So I'm going to read these questions out to you. What do we call the chemicals created after a chemical reaction? What do we call the chemicals created after a chemical reaction? Number 2, what is the law of conservation of mass? What is the law of conservation of mass? And number 3, what is the chemical symbol of normal table salt? What is the chemical symbol of normal table salt? Okay, pause it there, have an attempt, and I'll go over the answers just now. So, what do we call chemicals created after a chemical reaction? We call them the products. Products, they are what are produced from the chemical reaction, and you'll have seen that in the experiment that I'm going to do. Or what I did, you have seen it already. What is the law of conservation of mass? Matter cannot be created or destroyed. In the experiment, you will have seen that we had measured everything before and after the reaction, and we should be within the same amount of weight because nothing's actually, they look different, definitely, but the same amount of molecules and atoms are involved. And the chemical symbol of normal table salt is NaCl, which hopefully you remember from our first few lessons is sodium and chlorine, which forms sodium chloride. And that's normal table salt. Okay, conservation of mass. This is the last lesson we're going to kind of talk about this. So the conservation of mass, you've seen the experiment now. Feel free, if you have the equipment, you saw it wasn't too hard to set up. But if you have the equipment, try it out yourself. Don't just take my word for it. This is the whole point of being a scientist. We'll probably do this again in class when you guys return to school so we can do it properly in the lab. But what I want you to do is go through your workbook. You should have this in your workbook. You're going to work through this and you're going to attempt these questions yourself. Okay? So the law of conservation of mass. We have some blank letters here. We have a word bank on the right hand side. I'd like you guys to look through the questions on your own and have an attempt, and we'll go through them together now. So, the blank between baking soda and blank does obey the law of conservation of blank. Okay, the blank between baking soda and blank does obey the law of conservation of blank. So what were we looking at? Well, we're looking at a reaction, weren't we? So the reaction between baking soda and what did we look at? It would have been vinegar. It does obey the law of conservation of mass. Okay, so we would have weighed the baking soda, we would have weighed the vinegar before the experiment, the reaction. We conduct the experiment and then we weigh everything again afterwards. And we should be fairly accurate that yes, it does in fact obey the law of conservation of mass because the mass does not change. Even though the reactants and products look kind of different to one another, once the chemical reaction takes place, the mass, the weight of the experiment hasn't changed. The LCM, the law of conservation of mass, states that matter cannot be blank or blank. Hopefully you're very familiar now with the law of conservation of mass. It states that matter cannot be created or destroyed. Should be a full stop here. We're missing some full stops. It's okay. That means that the mass of a blank should equal the mass of the products at the start of the experiment. That means the mass of the blank should equal the mass of the products at the start of the experiment. So we know products on the right hand side of the equation, they are what are created by the chemical reaction. So what are the first things called? Well, they're called reactants. Okay, hopefully this is old news to you now. The reactants on the left hand side, chemical reaction produce our products. So I'm going to leave this blank because you will have this record in your book. I currently don't have that because I have not done the experiment yet. I did it last year, but I've not written it down anywhere. So you fill in the grams of the reactants. So how much did the vinegar weigh and how much did the bicarbonate soda weigh, or the baking soda. And after the reaction, there was blank grams of product. What was the total number of grams after it again as well? So you need to fill that in after you've watched my previous video. These masses were very similar / the same. Therefore, the blank obeyed the LCM, the law of conservation of mass. And that is the masses are not the exact same because of experimental error. If there is a little bit of a couple of grams difference, that's okay. That's probably just my fault as a human. If it was done by a robot, you'd probably see identical. But they should be fairly close. The last one then, therefore, the reaction obeyed the law of conservation of mass. So it's a nice, easy, simple experiment that demonstrates this really important law. And 2 lessons ago, we discussed phlogiston, and the law of conservation of mass essentially allowed us to kind of get rid of that theory that was incorrect because we knew that things had to weigh the same. So that was Anton Lavoisier. Okay, you'll have these questions in your workbook. Again, I'd like you to pause the video here and try these on your own. It's always best to try them on your own. If you don't get it 100% right, that's okay, but we can come back and talk about it. But I'm going to go through them now. So if you pause it here and at least give them an attempt. Okay, question number 1. Atom and mass conservation. Consider the following reaction between carbon dioxide and hydrogen. So we have the reactants on the left-hand side. You can see carbon is represented by the black sphere, oxygen by the grey sphere, and hydrogen by the white sphere. So if we look at the first reactant, it says carbon dioxide, 1 carbon, 2 oxygen, carbon dioxide, CO2, plus hydrogen. So we have 1, 2 hydrogen, equals, what does this equal? So we're going to name the products on the next slide. So name the reactants of this reaction. So I've just done that there. So we have 1 carbon and 2 oxygen plus 2 hydrogen. So we have carbon dioxide and hydrogen. We know that. And it says name the products of this reaction. So we have 1 carbon and 1 oxygen, and we have 1 oxygen and 2 hydrogen. So we have carbon monoxide, 1 monoxide. Even if you just wrote CO, that's fine. But carbon monoxide, which is lethal. I think it's an odorless gas. I'm pretty sure it's odorless. And if you breathe that in, it will kill you. So there's been some tragic events that have happened where sort of heating ventilation systems have been leaking carbon monoxide, and it can kill people if it comes into contact. So you might see more recently, particularly I've noticed it moving to Australia, particularly if you're renting somewhere, new rental places have to have carbon monoxide detectors in them as well, not just smoke alarms. And that's because we can't smell it. It's not like the gas that comes out of your oven or your hobs, I should say. So carbon monoxide is really deadly. Carbon dioxide is what we breathe out. So the difference of 1 oxygen really changes the properties of that element. Okay, so hopefully that makes sense. Balancing the equation. So we did this a few lessons ago. The following diagram models a chemical reaction, but the equation is not balanced. Explain why this equation is not balanced. So let's look at the chemical equation. What do we have here? We have hydrogen, which is represented by white spheres, and we have oxygen represented by the grey spheres. So we have 1, 2 hydrogen and 1, 2 oxygen. But the chemical reaction on the right hand side, it shows 1 oxygen and 2 hydrogen, so H2O, so it's making 1 water molecule, but we're missing an oxygen here. Okay, yep, we've got 2 hydrogen on this side and 2 hydrogen on this side, but we've only got 1 oxygen on the products, whereas we have 2 oxygen in the reactants, so we have to have oxygen in this side. So 1 oxygen is missing from the products. That's fairly obvious. It says draw in extra molecules in this diagram above to balance the equation being modelled. So I'd like you to do in your books is draw out this reaction, and the extra thing missing is 1 oxygen. So you'll have something that looks kind of like this. So we have H2 plus O2 equals H2O plus O. Okay, so we've drawn out the atoms, but you could write that as a chemical formula as well. Okay. Right, so now we're going to look at some formulas using these word equations. Okay, so we've got a bunch of chemicals here. So calcium oxide, which is written, the chemical formula is 1 calcium and 1 oxygen, CaO, 1 calcium, 1 oxygen. You have sodium carbonate, which is sodium, 2 sodium, 1 carbon and 3 oxygen. So sodium carbonate, so there's 3 elements in that. Calcium nitrate is calcium, nitrogen, oxygen, 3 oxygen and times 2 NO3. So calcium nitrate. We have hydrochloric acid. Hydrochloric acid is a really, really strong acid, and it's actually the same acid that you have in your stomach. And we're going to be talking about that quite a lot in the next couple of lessons. Hydrochloric acid, so we look at the name. Hydro is hydrogen, chloric acid, it's got chlorine in it as well, so HCl. Nitric acid is 1 hydrogen, 1 nitrogen, 3 oxygen. Sodium chloride, which we've talked about already, should be familiar with you, is salt, remember? 1 sodium, 1 chlorine, sodium chloride. Ethane is something we haven't mentioned before. Ethane is a gas. C2H6, so it has 2 carbons and 6 hydrogens. Acetylene, depends how you pronounce it. Acetylene, is how I pronounce it, is 1 carbon and 2 hydrogen. And then we have calcium carbonate, which is Ca, 1 calcium, 1 carbon and 3 oxygen. Okay, so you can see the carbonate here is similar to sodium carbonate. It has the last part is similar. Okay, that's the carbonate part. And then sodium comes from the sodium and the calcium comes from the calcium. So what I want you to do is you're going to write down a formulated equation. So I've got it here already. You're going to have a blank table, and I want you to work through this as I go through. So what do we have here? I just really want you, we're not worried about balancing it at the moment. I just want you to get familiar with, when you see these words, okay, it's quite nerve-wracking when you see all this, you're like, what the heck does this mean? And then when we write out the chemical equation, you're kind of like, okay, it's just calcium, it's just oxygen, it's just nitrogen, all added together. So the first one is calcium oxide plus nitric acid. So calcium oxide is up here, so you find calcium oxide, CaO, plus nitric acid, which is HNO3. So all I want you to do is calcium oxide plus nitric acid, just write that in. Calcium oxide plus nitric acid. And then the way that we write a chemical equation is we have this little arrow. The arrow represents the chemical equation. And now we need to see the products on that side. The products are calcium nitrate here and water. So water is not on the table, but we know water is H2O. So what I want you to do is write out that formula equation. So calcium nitrate is Ca brackets NO3 close brackets 2 plus water, which we know very familiar with, H2O. The next one I want you to write out, sodium carbonate plus hydrochloric acid for the reactants. So on the left-hand side of the equation, you're going to write sodium carbonate. Sodium carbonate, you're going to find it up here, is Na2CO3 plus hydrochloric acid, HCl plus HCl equals, when the chemical reaction will result in these products. The products are sodium chloride, carbon dioxide, and water. So you know sodium chloride, but we've got that in the table. So sodium chloride is NaCl. We know carbon dioxide is CO2, and we know water is H2O. And the last one I want you to write down is calcium carbonate. which is here. CaCO3 is the reactant. And when that reacts, it can create calcium oxide. We can break that down into calcium oxide and carbon dioxide. CaO plus CO2. So the whole purpose of this, I'm not expecting you guys to feel like, okay, I can go and do this and make loads of different equations. The whole purpose of this exercise is just to get you guys comfortable with when I talk about calcium oxide, sodium bicarbonate, calcium nitrates. That, for me, when I was doing chemistry, was really off-putting. And then I was asked to balance the equations and do all this complicated stuff, and I just really learned it. All I want you to do in this exercise is literally just write down what I said. I want you to feel comfortable with understanding that these long, often intimidating-looking names can be broken down into the chemical elements that they're made up of, and we can put them into these formulas, okay? I'm not expecting you guys after this to go off and I'm going to say, okay, go and do sodium carbonate and acetylene plus ethane equals what? Okay, you can do that if you want. Go off and do some extra homework, but I don't require you to do that. I just want to make you guys feel comfortable about writing out some of these complicated looking chemicals. Okay. Well, it's important, I think, when we talk about chemicals, how are they used in real life? So I talked about calcium carbonate a lot there, and calcium carbonate is used in agriculture to neutralize soil. And I'm going to talk about neutralization. So neutralization is related to pH. You may have heard of pH before, you may not. That's okay. That's going to be our next lesson. But pH is related to how acidic or how alkaline, which is the opposite of acidic, something is. So in the case of calcium carbonate, if you're a farmer and your soil is really acidic, it's going to be very difficult for you to grow crops and get a good yield. So what you want to do is make it less acidic, and to do that you can use different chemicals that can balance out or neutralize the acidity in the soil. So calcium carbonate is used, you can see the photograph in the top right, is used a lot on acidic soils to balance them out and help farmers grow crops. And rather confusingly, it's known as lime. It's nothing to do with citrus fruits or the green fruits that you put into salads or anything like that. It's called lime, but it's nothing related to the fruit. So you may have heard of that before, people using lime to neutralize a farm. If anyone's got any family members or friends that own a property who grow crops, you might have heard of this. Acetylene is used for welding and cutting. So if you've ever seen somebody welding before, welding is where you literally melt metal together. So you may weld, if you look even on a metal table, you see the legs have been welded on. Okay, you'll see that almost, you can see where it's been melted in the corners. And obviously to melt metal, you need to have something that's really, really high temperature. And so welders use these blow torches, but what is actually they're using is acetylene, and it is producing one of the hottest flames that we know about. So that's really good when you're trying to melt metal. So you might not have heard of that, but you've definitely seen people welding, or you've definitely used furniture that's been welded together. Your car would have been welded together, things like that. And finally, nitric acid is a really interesting one. I was watching a Netflix documentary it's called the Unabomber. I hadn't heard of this guy. It's crazy I hadn't heard of him, but this guy in the United States was trying to blow people up and blow things up, and he had a lot of plant fertilizer. And the reason he used fertilizer was nitric acid is used in the production of ammonium nitrate for fertilizers, but you can extract that nitroglycerin, and that is an explosive that can be used in TNT and things like that, which is crazy. And there was an explosion, I think it was in Spain. The big orange cloud, that's not green. Orange cloud, maybe I didn't get my eyes tested. The big orange cloud there was an explosion from a fertilizer factory, and it produces this horrible chemical that went into the population. So, it's amazing that some uses of chemicals, you're using them for fertilizers, but they can be used for other things if you know anything about chemistry. So I'm definitely not advocating you go off and make explosions using fertilizer, but when you know the chemical properties of elements, then you can put them to other uses. So not just fertilizers, but acetylene for welding, for example, calcium carbonate for neutralizing soils. So I thought they were interesting real-world examples of some of the chemicals that we just discussed. Okay guys, another interesting fact, the platypus doesn't have a stomach at all. Their esophagus goes straight into their intestines. That's amazing. I'm reading a book at the moment where it's talking about how humans have massive brains, and it said that we would have had large intestines when we were foraging and eating a lot, chewing a lot of food. The bigger your intestine usually means that you're breaking down a lot more food. And what they discovered is when humans domesticated fire, so I guess we're related to phlogiston, and we're relating it to the next couple of lessons. I'm talking about the chemistry of eating. Then our intestine, well, we didn't need to chew our food as much. We could cook our food and soften it up. So if you think about eating raw vegetables, it takes a lot longer than eating a cooked carrot versus a raw carrot, because the cooked carrot is softer. So when we started cooking our food, there's a theory that our intestines became smaller because we didn't need to take as long to digest it. And because our intestines became smaller, our brains became larger, because it takes a lot of energy to grow intestines. So if we don't need to spend all that energy in our intestines, then we could use that energy elsewhere in our bodies. So that's an interesting theory that you maybe want to check out as well. Thank you guys. We'll see you in the next one.